Okay. So before we talk about that that thing that looked like bunch of garbage, and it kind of is bunch of garbage because who knows what that memory address is? It's just memory address. But before we talk about this, let's talk about binary numbers. Earlier on, I told you that that array of memory that we kind of trying to imagine, starting from 0, can store binary numbers. Simply, there are wires inside the computer, and each wire can have different electrical potential, and that represents 0 or 1. So computer can really store individual, binary numbers which are zeros and ones. It's just the way it's designed right now. Okay, so that may change in the future, but for now, we have 0 and 1s that the computer internally understands. Okay, and these are just wire connections between different, circuitry in the computer. But they're all zeros and ones. Now, the decimal numbers look like this: 0, 1, 2, 3, 4, 5, and we just look at positive values starting from 0, right? So the binary number would be 0, 1, and then there comes 10. Of course, it's not 10. It's 1, 0, but because there's only 2 digits, 0 and 1, we run out of digits very soon, right? So decimal 2 is 1, 0 in binary world. Then decimal 3 is 1, 1. And again, we run out of possibilities and digits, and we have to switch over to 100, but of course it's not 100, it's just 4, right? So binary numbers really quickly gain the size, right? So if you look at number 120, it's going to look like pretty hefty number in binary world. In fact, we can go to a calculator, right? Do I have access to calculator? Right here, right? So this is a calculator. I encourage you to use it. And you would normally switch to a programmer mode for your calculator, so you get access to all of these wonderful things. And one of the things that I shut off here immediately is like this Q word. Q word stands for quad word. Okay, so D word stands for double word. But if you notice the difference, is all of a sudden there's less stuff printed in this area. When you switch to a word, it gets shorter, right? And when you switch to a byte, it gets even shorter, this little area. So let's start with the byte. So like I said, if I punch in something like, by the way, staying in decimal world, which I am most comfortable with, right? Just say 120, right? And then if I switch to binary, okay, that's some number, or I can see the individual numbers here. So you can see that in binary world, 120 is this, like 1110000, whatever that is, right? So it's a really, is it human friendly? No, it's not. Like, if you can, I don't know, if you can. I cannot memorize for longer than like 1 second that this is 120, right? If I walk out this door and you ask me, so what was that number? I'll tell you I have no recollection, okay, because it's just overwhelming and unfriendly. Okay. So binary numbers and computer architecture, okay, another thing for us to look at. The internal use of binary numbers forces computers to manipulate types of data that have certain sizes. When you look at these typical sizes of data, like this byte or word, which is like 2 bytes, or D word, which is like double word, you see that the number of these binary digits increases. So let me switch back to a byte. Byte is 8 bits in size, and it's not coincidental because the number 8 is a power of 2. Powers of 2 are 2 raised to the 0th power is 1. 2 raised to the first power is 2. 2 raised to the third power to the second, to square, second power is 4, then 8, 16, and so forth. So in computers, the sizes of data are typically the number that corresponds to a power of 2. So 8, 16-bit, 32-bit, 64-bit are those that are computer friendly. Unfortunately, 10 bits, which would be perfect for decimal world that we live in, pretty much, right? 0, 1, 2, 3, 4, 5, 10, 11, and so forth, is not very computer friendly, because when wires inside computers split, okay, when you have this, some kind of circuitry inside your computer, and let me just get rid of that, right? So you have some wires. So here's one wire, here's another wire. But typically, what happens is that these wires can split like this, right? And you go from 2 wires over here to 4 wires over here. So this is 2, and they become 4. And that's the world. If we keep splitting, we're going to get like 8 and so forth. So they're multiples of 2, but they're also, we formally say, powers of 2. So that's why, for instance, a 64-bit is one of the very popular data types, right? But it's a multiple of 2. In fact, this is 2 raised to the 6th power. Why? Because it's like 2 multiplied by itself 6 times, okay? By the way, the binary value of 64 is this, 1000. Okay, so binary numbers in humans, we already said that something like 1, 2, 3, 4, 5, 6, which kind of okay, if I told you that's a decimal number, looks like this in binary world, and we can say, arguably, this is not very friendly. So because we have 16-bit, or 32-bit, or 32-bit numbers typically used, what we use most commonly to refer to locations in memory, we either use actually octal numbers, mostly used in device drivers, because in device drivers sometimes you manipulate 2-3 bits only on the controller of that device, and octal numbers are basically numbers that basically go 0 through 7, and then you run out of digits, and the next number is 10, because there's no digit 8, okay? And octal numbers perfectly describe, quantities of all together, put together with just only 8 digits. 0 through 7, altogether there's 8 digits, and these are octal numbers. Now the hexadecimal numbers, however, are more convenient because they can quicker describe bigger quantities, such as this crazy number. It's a hexadecimal number. Okay, and so hexadecimal numbers are quite the opposite. If in decimal world we can count on till 15 like this, these are 16 digits, 0, 1, 2, 3, all the way through 15, altogether 16 digits, okay? The hexadecimal notation, and basically 16-based numbering system, what it does, it's just like decimal world, it's using digits from 0 to 9, and then it says, oh, we ran out of digits, so how do we compensate, because we need 16 digits to use hexadecimal number, we need 16 digits. So it's compensated by adding A, B, C, D, E, F characters or letters, right? So these are digits in hexadecimal world. And so therefore, put all of this together. I just want to show you the once it loads perfectly, I just want to kind of demystify for you these notations very quickly. So this is all familiar decimal numbering, and we have a sample from 0 to 15, altogether 16 numbers, okay? 16 altogether, including 0, because 0 is also very important to us, right? So in hexadecimal world, number 11 is simply B, okay? Number 13 is D. Number 4 is 4, because we have these digits, hexadecimal digits, that run from 0 to F, okay? Then in octal world, these numbers will be encoded like this, and if you watch them carefully, after 7 comes 10, okay? And then basically after 17, there will be another, like 27 coming over. But in the binary world, 0 is all zeros, 1 is 0, 0, 1, 2 is 1, 0, and basically we begin to exhaust all combinations, and it just happens that at the position number 15 on our row, all ones here represent the last combination we can possibly get from 4-bit combinations of zeros and ones, right? So from here to here, from 0 to all ones, all combinations are exhausted. So now, if you, let me just use some kind of space, perhaps right here, right? So if I just type it in here, I can make this visible. So I'll just say, let me just take a snapshot of this. Okay. I'm trying to see where my keyboard keys are. Okay, so I have some kind of help from this view right here, and so for me, if I wanted to go from this crazy number like 7, 9, 8, and so forth, all I have to do is say 7 happens to be, if I increase the size of this just a little bit to make it all visible and make all of this like visible on one screen, I can say that 7 is 0, 1, 1, 1, okay? 9 is 1, 0, 0, 1. And so therefore, I can take this hexadecimal number and this set of binary numbers and very quickly convert that crazy number to a binary number, okay? So hexadecimal numbers are simply very convenient way to express really binary numbers, but in much more condensed format. All they do is that every single digit in this hexadecimal number is basically a combination of zeros and ones from over here, right? So if I have B or C, so B would be 1, 0, 1, 1. So therefore, all I have to do is like replace each digit by 4 binary digits. And more so, if I take this quickly into my calculator, Control C, and I still have my calculator, and I say clear, and I switch to quad word, which is 64-bit world, and switch to hex, and simply Control V, paste this in, I can convert it to decimal number, or I can convert it to a binary number just using the calculator very quickly, right? So let's just remember that hexadecimal numbers are used to express memory addresses, and this would be the last thing I wanted to share with you today. So we meet again. Watch what I post on the website. First quiz is going to be available sometimes later this week. This recording is going to be also posted on YouTube. The link will be added to the website, and I'll see you guys tomorrow in Java class and also next week in CIS 123.